Welcome Regents students. This is the final video in our modern physics unit, and the topic is called pair production and pair annihilation. As I mentioned in the previous videos, if you were to shrink yourself down to smaller than an atom and watch what was going on with the particles around you, electrons, protons, and neutrons, the goings on would be very remarkable. In fact, if the same things that happened at that level happened at the macroscopic scale in terms of things that we can see, like my hand or pens and pencils, we would label that as magical. Today's topic, today's phenomenon, is no different. To illustrate that point, I want to just talk a little bit about a classic book, Mary Shelley's Frankenstein. So you probably remember the story. In this novel written in 1818, Dr. Frankenstein constructs a monster out of body parts. He sews together arms, legs, heads, a head, and then he animates this creature with electricity. And it was a terrifying story at the time because it was like kind of a magical effect where the monster was, the body parts were brought back to life with science. What we're going to learn today is beyond that. Imagine that Dr. Frankenstein wasn't even constrained in his experimentation, his gruesome experimentation, with the requirement of finding body parts to sew together. Imagine instead the lightning bolt came down and the empty table suddenly had a body on it that was alive. So we would recognize that that would be even beyond the imagination of the novelists at the time, okay, if Dr. Frankenstein could do that. We're going to see that that's what we're going to be looking at today, the phenomenon of things being created from energy alone, matter being created in pair production. Then we're going to see matter being eliminated in a process called pair annihilation. So what is pair production? All right, so in pair production, what you have before the event, the production event, is you have a photon. Remember, a photon is vibrating electric and magnetic fields at a particular frequency. Remember, we have this electromagnetic spectrum, and if we take any object, such as this pencil, and rub it with fur and make it charge, and then we wiggle it, we would create vibrating electric and magnetic fields. And depending on the frequency at which we shook the pencil, we could create different kinds of electromagnetic rays. If we shake very fast at high frequency, we can create X-rays or gamma rays. So I shake and I make electric and magnetic fields, like a kind of similar to a lightning bolt, as electrical effects. And so that's the photon, high energy, either an X-ray or gamma ray on the left side of the electromagnetic spectrum, the highest energy photon possible. This photon comes in and hits an atom, a nucleus, that's just sitting there. And then what happens is the photon disappears, and then what comes out after is a particle. In this case, I wrote E minus for an electron, and an E with a bar over it indicating the antiparticle of an electron, which we don't call an anti-electron. It's the one exception where we don't call the antiparticle, we call it the positron instead. So we got an electron and positron, matter and antimatter. And then in the presence of a magnetic field, we can get these to spiral away from each other, and we have now a particle and the antiparticle. Again, this appeared out of nothing but electromagnetic waves. So I produced matter, real physical things, out of just this energy of the photon. So let me go on with the physics a little bit more. When that happens, both momentum and energy are conserved. Also, charge is conserved, by the way. Notice I have zero charge before, and then negative and positive, I have zero charge after. But momentum, Pi equals Pf. Where was the momentum before the the electron and positron were created, it came from the photon. Remember, a photon has energy and momentum. So the photon is like a tiny submicroscopic bullet that comes in with momentum, and then after, the momentum cannot disappear. Pi equals Pf. So the momentum after, when the photon goes away, is now present in the electron's momentum and the positron's momentum. Okay, so that's a key idea. But it doesn't help us in our calculations. The idea that really helps us in our calculations is this one, that the energy must also be conserved. And I should say, we don't mean like energy in the old sense, we mean mass energy, where mass can appear as long as energy appears, and vice versa. So what we have before in terms of energy is the energy of the photon here, and as we know from the reference table in the modern section, the energy of a photon is either hf or hc over lambda. So we could have had hc over lambda here also. So that's what we had before for energy. After, when the photon disappears, we've got the energy that's associated with the mass itself, mc squared. Right? So for the electron, E minus mc squared, and m for the c squared for the positron, and each have kinetic energy also. Now we're going to assume the kinetic energy is negligible, so this would represent the minimum energy necessary for coming from the photon. And so what we have on this side, because the electron and the positron, every particle and antiparticle have the same mass but opposite sign, these are the same m's, we could combine this side to 2mc squared. So now what you can see is that you can calculate the minimum frequency necessary to produce an electron and a positron by simply plugging in Planck's constant here. Okay, Planck's constant, front cover of the reference table right here, near the bottom of this first table, H, there it is. You plug that value in right here, okay? And then right here, and then the mass of the electron and positron, well, you look up the mass of an electron, rest mass of an electron, 9.11 10 to the minus 31, and you plug that in there. Speed of light, that's right here on the reference table, speed of light, 3 times 10 to the 8th, and you could solve for the frequency necessary to produce an electron and a positron. So that's it. You just need a certain high enough frequency of X-ray or gamma ray to produce a certain subatomic particle, proton, electron, or neutron. So back to our book here, as I mentioned, Frankenstein. So now imagine if I were to write a book that's similar to this. I could have a photon electromagnetic energy coming in instead of my lightning bolt, and then I create an electron and a positron, and I spiral them away from each other with a magnetic field. I use other photons, I build protons, neutrons, and eventually I build atoms over here. I maybe make an oxygen atom with the electrons, protons, and neutrons. I build a carbon atom, a water molecule, and over here, with the anti-electron or positron and the anti-proton, anti-neutron, I build my own set of mass over here, and I keep them separate. And then I construct a Frankenstein monster over here out of this matter, and a Frankenstein monster over here out of this antimatter. So I could make two monsters on two separate tables just from the energy. Where there was an empty table, suddenly I have matter that, boom, right there, appears. And then the monsters can be, the monster can be horrible, like in the book. The anti-monster could be horrible, like in the book. And then here's an added twist. What we're going to see in the next section, I mentioned briefly when I talked about antimatter. When antimatter touches matter, it makes the matter and the antimatter disappear, cease to exist, and in the process, energy is released as mc squared. So the monster and anti-monster have to be kept separate, even away from the atmosphere, and then when they come together and touch, the two monsters explode and destroy the United States in a big giant crater, right? So this is actually, far more reaching than the Frankenstein novel, and yet, in theory, it's possible according to the physics, creating matter and antimatter from photons. This really happens. It happens in experiments. Not obviously, we don't make Frankenstein, but we just make these little particles and antiparticles, and all from energy. You're making matter appear out of nothing, and again, it's almost like a magical effect. All right, so that's pair production. The key idea is momentum's conserved and energy's conserved. HF is mc squared and mc squared, giving us this. We could calculate between frequency and mass. Okay, so the next topic for today is pair annihilation, which I already mentioned. So let's move on to that. Okay, so now I have my particle and antiparticle, and as I mentioned, when an antiparticle touches the particle, they cease to exist and give off pure energy in the process. So what happens is the electron and positron disappear, and now what happens, instead of one photon appearing, two photons appear going in the opposite direction. Why is it necessary to have two photons, where over here we had one photon making the two particles? Here we have the two particles making two photons. The reason for that is that momentum must be conserved. Before, if these are not moving, there's zero momentum in the system. MV, nothing is moving. So if there's zero momentum before, there must be zero momentum after. If there were only one photon, there's no way for there to be zero momentum, because a photon has momentum no matter what. It cannot be stationary. It moves at 3 times 10 to the 8th. So we need at least two photons created for the momentum to be zero. I suppose we could have 3, right, going off in all directions, but you need it more than one so that they add to 0. But this would be like maybe -2, +2, adding to 0 momentum. So that's the first thing. 2 photons must be created because of momentum being conserved. That's why I highlighted that, to emphasize that. The next calculation is that energy must also be conserved. So what we have in the beginning is the mc squared and mc squared, the rest mass energy of the two particles. The mc squared for the electron, the mc squared for the positron. They may have kinetic energy before, so that's another energy that might be before. After, there's no more mass, no more kinetic energy, because they're gone, the particle and antiparticle. So what we have are the energy hf or hc over lambda for the two photons. And then so you see these masses being the same, electron, positron, we've got 2 mc squared on this side and 2 hf on this side, assuming negligible kinetic energy. And so here we've got a relationship for a certain mass of particle and antiparticle eliminating themselves. We can calculate the frequency of the photons released. So that's pair annihilation. Again, another remarkable effect beyond, right, the fiction writers and the horror writers. You can have matter created from just electromagnetic energy. We make particle, antiparticle, all right, and we could calculate the frequency necessary for that. Or you could take the two particles and antiparticle and make them disappear into nothing but energy. Poof, they're gone, and energy released. And the main calculation, mc squared before, hf, energies after, set them equal, and you get an expression where you could calculate, say, the frequency generated by certain masses annihilating themselves. All right, so that is the last topic in our modern physics unit. And maybe I'll make some review videos in the future for the end of the year. But if not, then I hope to see you in class again. But if it doesn't happen, then you know, unfortunately, maybe I'll see you next year when all this stuff clears up with the virus. All right, so thank you for watching, and hopefully I see you soon.